Good morning, students. In the session 26 of the e-content program, continuing with the topic crystal field theory, today's class we will be discussing the factors affecting the magnitude of splitting. In today's class, we are going to consider the factors affecting the magnitude of splitting. The magnitude of splitting in case of octahedral one is represented as delta O. This dictates whether the complex with 4, 5, 6 or 70 electrons is high spin or low spin, which affects its magnetic property, structure and reactivity. So the magnitude of splitting in an octahedral field with a complex having 4, 5, 6 or 70 electrons is high spin or low spin, and this is going to affect the magnetic properties, structure and reactivity. If the splitting is going to be larger than the pairing energy, if the splitting is going to be larger than the pairing energy, it is going to yield a low spin complex. Whereas if the splitting is going to be less than the pairing energy, P actually stands for pairing energy, it is going to produce a high spin complex. Now, coming to the magnitude of the splitting depends on the following factors. Coming to the factors in which the splitting depends is going to be, first is going to be the nature of ligand, oxidation state of the metal ion, size of the d orbitals, that is transition series, geometry of the complex. So, the four important factors are going to be nature of the ligand, oxidation state of the metal ion, size of the d orbitals, geometry of the complex. Now, let us study one by one each case. So, slowly let us go on to study in detail all these four factors which affect the magnitude of splitting. Coming to the nature of ligands, greater the ease with which ligands can approach the central ion. If the ligands can approach the central ion easily, the greater is the crystal field splitting caused by it. So, the ease with which the ligands can approach the central ion will make the crystal field splitting greater. The ligand with large negative charge, small size and having good sigma donor and pi acceptor power will give large crystal field splitting as they can approach the central ion closely. Here, what do we observe is, if the ligand is going to have high negative charge and it is going to have small size and it is a good sigma donor and a good pi acceptor power, will give the crystal field splitting, and they can, because they are going to approach to the central ion closely. For example, the crystal field splitting delta naught values for halide complexes generally decreases of the odd. Fluoride is going to have greater than chloride, which is going to be greater than bromide and iodide, because smaller localized charges such as F interact more strongly with the d orbitals of the metal. Because of the small size of the fluoride atom, it is going to interact strongly with the d orbitals and there is going to be a greater splitting. In addition, a small neutral ligand with a highly localized lone pair such as ammonia molecule. Ammonia molecule is going to be a neutral ligand and it has got highly localized lone pair of electrons. This also is going to significantly larger delta values than might be expected. This is going to be greater than what is expected, and the main reason for this is the lone pair points directly to the metal ion, because here the lone pair of electrons over this molecule is going to point directly to the metal, and the electron density along the metal ligand axis is going to be greater than for a spherical anions such as fluoride. So this is because it is going to directly point towards the metal ion. The electron density along the metal ligand axis is going to be greater for a spherical anion such as fluoride. The next one is going to be the oxidation state of the metal ion. The metal ion with higher oxidation causes larger crystal field splitting than is done by the ion with lower oxidation state. That is, metal ions which has got higher oxidation state is going to cause a greater or a larger crystal field splitting than the one with a lower oxidation state. For example, if we are going to see, that is cobalt in +3 state is going to have a greater crystal field splitting. That is, it is going to be 18,600 centimeter inverse, whereas the crystal field splitting in the +2 oxidation state is going to be only 9,300 centimeter. So with a higher oxidation state, there is going to be a greater crystal field splitting. So oxidation state is going to be one of the factor which is going to affect the magnitude of splitting. Another factor is going to be the size of the d orbitals, that is the transition series. For a series of complexes of metals from the same group in the periodic table, for a series of complexes of metals from the same group in the periodic table, the same charge and the same ligand, when there is going to be same charge and the same type of ligand, what do we observe is the magnitude delta naught increases with increase in size. As the size increases, what do we observe is the splitting is going to be greater. That is, 5D transition metal is going to have a greater splitting than 4D, which is going to be greater than the 3D. One such examples which we can take is, that is, I am going to have the same charge, same size and the same ligand. Here I am having the same ligand, ammonia molecules are the ligand, and charge is going to be the same, but only the size is going to vary. As the size is going to increase, what do we observe is, we observe that the splitting is going to increase. In case of cobalt complex, what do we observe? The splitting energy is going to be 22,900 centimeter, while for rhodium complex it is going to be 34,100 centimeter inverse. In case of iridium complex with the same charge, it has 40,000 centimeter. The increase in splitting with increase in principal quantum number is mainly due to the large radius of the valence orbitals down the column. Apart from this, the repulsive ligand-ligand interaction are most important for small metal ions. This results in metal ligand distance and stronger d orbital ligand interaction. And for this reason, what do we observe is, that is, with increase in size, with increase in the size of the d orbital, the splitting is going to increase. Coming to the last, that is the geometry of the complex. The crystal field splitting energy of a tetrahedral complex delta T is nearly half the value of the octahedral complex. That is, delta T will be equal to -4/9 of delta octahedral one. As a result, that is, the splitting field depends even on the geometry of the complex. That is, the crystal field splitting energy of a tetrahedral complex is half the value of the octahedral complex. As a result, the splitting energy for tetrahedral complex in general is small compared to the pairing energy P. Tetrahedral complexes are therefore mostly high spin complexes. Thank you.